Welcome, sir, to this webinar.
Thank you, madam.
Okay. Dr. S.B. Banu Prashant, sir, is graduated from Siddhaganga Institute of Technology, Tumkur. Hello?
You continue, madam. Continue.
And pursued M.Tech and PhD at the Indian Institute of Science, Bangalore. He has 28 research publications in international and national journals and conferences to his credit, and has also co-authored a textbook on linear integrated circuits, concepts and applications. He has received research grants of 40 lakhs from VGST and DST. He is a member of the Institute of Smart Structures and Systems, Instrument Society of India, and currently the chairman of IEEE Censors Council, Bangalore Section Chapter. His special interests are in the domain of instrumentation techniques, analog circuit design, embedded systems, optical fiber communication, human body area network, and amorphous semiconductors. He is a recipient of the Dr. APJ Abdul Kalam Memorial 2018 Outstanding Teacher Award from the ISBR of Bangalore Educational Trust. He has 30 years of passionate experience in teaching and research. So, sir will be talking about the detection and quantification of small molecules has become an important necessity in most of the fields connected to human life. In this context, the biosensors have become very cheaper and faster alternatives chromatographic techniques. This talk provides a conceptual overview of the basic principles of biosensors, their desirable properties, and detection techniques. The evaluation of blood glucose biosensors will be considered as a case study. To conclude, the role and impact of nanomaterials in developing novel biosensing devices will be highlighted, considering two examples of quantum dot and nanowire-based biosensors for the detection of cholesterol and DNA molecules. Okay, sir. Over to you, sir.
Yeah. Just give me a while. I'll share the screen.
Okay.
Sir, can you see the screen? Yeah.
Yes, sir. It can be seen, sir.
Okay. I'll start my talk.
Yes, sir.
Yeah, so I thank all of you, the coordinators there, under the leadership of Dr. B.P. Harish, for the wonderful opportunity to share my little knowledge about the so-called biosensors, in which I'm going to give kind of a overview conceptually about this particular very interesting topic. I'm Dr. Banu from BMS College of Engineering. One second. Yeah, can you see the slide advancing, sir?
Yes, sir. Go ahead, sir. Yes, sir. Go ahead.
Okay. So this is how my presentation has been outlined. And I'll be first talking about the so-called small molecules, in which I'll give just an overview about the importance of the so-called small molecules after defining them. Then we talk about biosensors, wherein we introduce them and also tell you about the different components that are required to make a complete biosensor. Then we take the examples of the different types of bioreceptors, with one example for that matter. I'll take a very relevant example related to corona. And then I'll talk about the evolution of glucose sensor as a case study, in which I'll tell you about the 3 different generations of glucose biosensors, how it was all started somewhere in the 1950s or 60s. Then what do we have today in the market? Then I'll try to, touch upon the impact of the nanomaterials on the biosensor fabrication. And I'll take 2 solid examples. One is, a biosensor based on quantum dots that is used to detect the cholesterol content. The second is a biosensor based on the nanowires that is used to detect the DNA molecules. Then finally I'll conclude, and then if there are any questions, I'll be more than happy to take. Right, we'll go ahead with this. To define small molecules are the ones which are of very, very small size, like 1000 Dalton, around that. And just note how much is 1 Dalton equals to. It is 1.6 into 10 to the power of minus 18 micrograms. So small is a molecule, and 1000 times that is not going to make a big difference, but we do have small molecules everywhere for that matter, right? So these small molecules are found in variety of chemical compounds of both natural origin and the pharmaceutical origins, and they are very, very relevant both biologically, pharmacologically, and even environmentally. We have to deal with these small molecules. They can have both positive and negative impact, as all of us know about it, right? Like in bacteria, we have good bacteria and bad bacteria and things like that. And every human cell is a collection of 100 to 200 different types of low molecular weight organic molecules, like the so-called amino acids, or the nucleotides, or the sugars, and all their derivatives are very, very small molecules. Now that, they are being small, they are there everywhere, in our everyday life too. Anything that you talk about, we have to deal with these small molecules. So therefore, their detection and even quantification becomes a very, very important aspect of the scientists and engineers in almost every discipline that you can name. In fact, small molecules are big players. We don't want a better example than the coronavirus, which has become such a big player bothering the entire globe, being so small, right? So therefore, the detection and quantification of these small molecules is very, very important. And the standing out example is the coronavirus, right? So with this background of having defined small molecules, let us see how do we go about detecting the small molecules. It could be either detecting just to tell whether it is there or not, or it could be even to quantify them, that this is the extent to which this particular small molecule is present in a given biosample. The so-called chromatographic methods are the good old instrumentation technique methods with very huge desktop instruments like this that provide very high sensitivity and specificity. Down the line, I'll define what is sensitivity and what is specificity of a sensor all about. But it's very costly instrumentation and also very bulky instrumentation, and it's very time consuming and require expertise. You and me may not be able to operate an instrument like this because it requires that kind of an experience to deal with this particular very expensive instrument. And also they're less suitable for every purpose. The way you use your glucose biosensor, you can't use these particular instruments. They're not handy, they're not portable, they're fixed in a particular laboratory, and it requires an expertise to, get the sample in and the results out and so on and so forth. They have got their own set of disadvantages. But the biggest advantage...
One second, sir. Slides are not changing. Check it out, sir.
One second, sir. That's what I was trying to ask you. 1 second, sir. I was trying to share. 1 second.
But the slides is coming to display, no?
Okay. 1 second.
Okay.
Now can you see, sir?
But slide is not displaying. Bhanu Prashant is starting to share content that is showing, sir. Yeah, sir. No displaying, sir. No displaying.
Small molecules you can see?
Yeah, sir. Small molecule you are seeing that.
Okay. Is it advancing also?
Yeah, sir.
Okay, fine, sir. I'm sorry, I did not know about that.
No problem, sir. No issues.
Okay. So we defined what small molecules are, and the detection of them is very, very important. And I took the example of the coronavirus, which makes detection and quantification of small molecules all the more important, right? Yeah. Sir, it's all clear now. You can see the fourth slide. Hello?
Hi, yes,
sir.
Detection of small molecules.
Yes. Yeah. Very good. Sorry for any inconvenience, because of this. Yeah. So these so-called the chromatographic techniques are the benchtop instruments that I was just mentioning about. They're very bulky, they're very expensive, and all of us will not be able to use it because it requires some expertise. And but the greatest advantage of these kind of instruments is that they give very high sensitivity and even specificity. But because of these disadvantages, people thought of coming out with other sensors. We call them as biosensors, which can offer very cheaper and very faster alternatives for the detection of all these small molecules. The figure that you can see here is the glucose, molecule biosensor, which is so handy, and most of us have such a kind of a biosensor at home. We don't have to run to the, biggest laboratory to have ourselves tested, and that's the beauty of biosensors. And they give these advantages like, real-time monitoring, then high specificity, then very fast response time within tens of seconds, and then reduced consumption of organic solvents. You don't require solvents to work with these biosensors, and they're very portable and cheap. And de-skilling. De-skilling means even a common man can use such a biosensor, unlike the, chromatographic instruments in which expertise is required always to work with this kind of instrument, right? So therefore, I'm trying to emphasize the importance of biosensors, which are of such a big use even for a common man, thanks to all these advantages, right? So having told you about the importance of biosensors, let us see how do we go about making biosensors. But before I talk about biosensor, just to have, you well connected, let me take, back to the basics in one slide, wherein I try to define what is called as a sensor or a transducer. And as all of us know, it's a device which is capable of being actuated by a measuring quantity, converts one form of energy into another more usable form of energy. So any device that converts one form of energy into another more usable form of energy, we popularly call it as a sensor or a transducer, right? And when it converts into a more usable form of energy, we prefer that to be an electrical output so that, you can manipulate, you can play around the electrical signals. For all the modern applications, we don't want the mechanical output as a signal, we want an electrical output. So I've shown three pictures, sort of three different kind of sensors, in which you have an LM35 sensor that converts temperature into a voltage with a sensitivity of 10 millivolt per every degree Celsius. So this is another temperature sensor called AD590, which will give an output current of 1 microampere per every 1 Kelvin change in temperature. So this is another sensor in which the resistance will change as a function of the force or pressure, whatever you apply. So all these three devices are converting temperature into voltage, temperature into current, and force into a suitable change in resistance, which can be changed into a suitable output voltage by putting that in a kind of a Wheatstone bridge circuit, etc., or any other technique for that matter. Anyway, I have just defined sensor, which converts one thing to another. Now to define bio, anything that is connected with the human life and its existence is what is called as bio, any living being. It's not only we, it could be any plant or it could be any beverage industry. Anything that is connected to the human life, we call it as the bio. And now let us see how do we make sensors that are applied or that are used by the human beings, we or anything around us. So to define biosensors are a class of sensor devices that can detect or quantify an analyte in a given sample. You have a given sample and you want to pick a particular analyte and either detect it or quantify that or make a measurement of that. Quantification is the process of associating numbers with what you don't know with suitable units, right? And what you're trying to measure could be an inorganic compound like a salt, or it could be a very small molecule like a vitamin or a sugar molecule, or it could be even larger biological macromolecules like proteins and nucleic acids and etc. Or it could be a pathogen like a virus and a bacteria that you want to detect in a given analyte, right? For example, if I give my blood sample, so that becomes my sample, and I want to, get the sugar, the molecules in that detected and tell whether, I'm diabetic, etc. and so on and so forth, right? And most of these biosensors for their operation exploit what is called as a biochemical interaction for their operation. For example, there will be, as I will show in the next slide, so there will be one bioreceptor onto which you put the sample. So there will be a biochemical or electrochemical reaction that is being happening. So that is usually exploited to make a measurement of the unknown quantity that you want to measure. So to summarize, any device that detects all the things that are connected to the human life and its existence and the surroundings, and especially the quantities that are extremely small, micro or even nano in nature, we develop a sensor, and that becomes what is called as a biosensor, which will always exploit a biochemical reaction for their operation. And this particular picture shows the simplest block diagram of a biosensor, wherein we have an analyte whose constituent is to be measured. And please notice here, we have used different types of symbols here. You have circles, you have triangles, you have square, and you have circles and so on. So this is what it means, that a sample can contain a whole lot of things. But I want to develop a sensor that will pick only the circular molecules, which are, say, the blood glucose samples in a given amount of sample, right? So that becomes my biological signal, which goes to what is called as a bioreceptor. The bioreceptor is already present in the sensor or the biosensor, and between the analyte and the bioreceptor, there will be that biochemical reaction that is happening, and that gives another signal, what is called as a physiochemical signal, which goes to any of the popular transduction technique that you and me, all of us are familiar with, right? And once the transducer gets that particular thing, you get an electrical signal, so that can go to the signal processing unit, and you have your biosensor, right? So to summarize, the analyte reacts with the bioreceptor through a biochemical reaction. So the bioreceptor gives some kind of a physiochemical signal that is picked up by a particular transducer to give an electrical output. Anything it could be voltage, current, frequency, charge, or whatever. So that goes to the signal processing unit where it gets displayed, right? Why did biosensors came to the market? So, to be very appropriate, the initial impetus for the advancing sensor technology came from the healthcare area. So it is, the whole of technicians wanted to better the human life for safe and comfort living, and they started inventing these portable devices to make the health better cared, right? And it all started with the measurement of blood glucose or the blood gases or the ions or the metabolites. Metabolites are the byproduct, the intermediate products of the so-called metabolism process that happens in the human body. All these things need to be measured, right? And all these measurements will give a better estimation of the metabolic state of a particular patient. So people started working on biosensor only for the healthcare unit in the beginning. But as in today, I'll show at the end of this particular presentation that biosensors are extensively used for various applications and in almost every domain that we can name, right? So this is what a biosensor looks like. It's now a very portable device. So it's a glucose monitor in which you put a drop of blood. So that becomes your sample, and the sample has an analyte to be picked up, and that is picked and measured using a suitable, technique, about which also I'll talk in the coming slide, right? Now let me take the example of a blood glucose biosensor. As you know, you have an analyte that goes to the recognition element, then the transduction element, and the representation. Now, the bioreceptor in a glucose biosensor is what is called as a glucose oxidase. Glucose oxidase is an enzyme that is already present in the test strip that you are trying to use or insert into the glucometer, right? Now, the glucose in the blood sample becomes analyte, and there is some kind of a reaction that is happening, and then the signal is going to the signal processing element. So then that is suitably calibrated, and then you represent the signal, and you have your biosensor, right? So the highlight of this particular, biosensor is the interaction or the reaction that happens between the analyte and the biorecognition element. This is true in all instrumentation system. We have to concentrate on the very first interface. Other things can be easily played around or manipulated, and most of the research is all about developing the novel techniques of detecting a given analyte using a different form of recognition element, and so on and so forth, right? So to match this particular block diagram on the left-hand side to the example of the glucose biosensor on the right-hand side, so there is a test strip here, which will have a pre-coated or a pre-fabricated, enzyme coated on that. In particular, this strip will have what is called as a glucose oxidase. And when you drop your, droplet of the blood on that, so there will be an electrochemical reaction on that. And what to do with the electrochemical reaction? What you can do is, you can either, find out the change in the color of the strip, and that could be an indication for glucose level, or it could be measured electrically also as the electrical current being produced by this particular sensor, and that's how all these sensors work, centered around the reaction between the analyte and the biorecognition element, which can be encached suitably or processed suitably, or the transducer picks a proper signal to give you an indication of the analyte that you are trying to measure, right? So that's about the glucose biosensor. Now, this is yet another block diagram to tell you about the components or elements of a biosensor, little exaggerated to get into more details of that. And as I showed you in the previous diagram, you have analytes that will interact or have a chemical reaction with the so-called bioreceptor. Please look at this. They're all in different shapes to tell you that what you measure could be different analyte. For example, it could be sodium, or it could be glucose, or you may be interested in H plus ions, what is the pH value, or it could be lactose, or it could be, calcium ion, or it could be potassium ion, and so on and so forth. Now, the bioreceptor is already present on the biosensor what you're trying to use, so that will have an enzyme or an antibody or a multi-organism, or even it can have a DNA chain as what is called as a bioreceptor, right? So we call them as molecularly recognizing elements. So these will have a specific interaction, specific bonding with what you're trying to measure, and that gives a different kind of a change, like it could be an electroactive substance, or it could be a change in the pH value, or it may produce heat as a function of this biochemical reaction, or there could be a change in the mass of it, or it may produce light, it may produce electrons, and so on and so forth. Now, once you get the signal into this particular form, it's all the more easy to measure this voltage using an electrode, or you can use a semiconductor pH electrode to know what is the change in the pH, or if it is heat produced, you can use a thermistor, what is known to us, to pick the changes in the temperature, or if it is a change in the mass, you can use a piezoelectric device, or you can use a photon counter if it is light, and now it becomes a measurable signal in the kind of an electrical signal, so that can be suitably amplified, go to the signal processing circuit, and then the interface, and you have the biosensor in your hand, right? So this need not be a big-end computer always. All these biosensors will have very portable, low-power microcontroller embedded into that, so that it becomes very portable and handy, right? So, these are the different components of that. And look at this, the analyte what you're trying to measure could be, any one of this. It could be an RNA, DNA, or you may be interested in measuring a toxin material, or you may be interested in knowing an antigen or an antibody, or viruses or bacteria, or you may be interested to know what is the pH of my solution, or you may be interested to know the number of cations or the anions in a given sample, or it could be anything that you want to measure. Now that goes to the bioreceptor, which is also called as a biorecognition element, which could be anything like an enzyme, or it could be an antibody, it could be an antigen, or it could be tissue, cells, bacteria, yeast, and even nucleic acids, or even biomimetic materials like aptamers and ribozymes, which are man-made materials. Ultimately, all these biorecognition elements will have some kind of a very, very specific reaction with the analyte, giving to one of these specific changes that can be easily picked up by one of the transducers like this. So then the life becomes very easy. So now change upon the recognition element could be a product or a reactant, or a change in the pH, or it could be redox activity in which the electrons are gained or lost, or it could be an electron transfer, or it could be change in the heat or capacitance, or change in the mass, or it can produce an electrical potential, current, conductance, or impedance, viscosity, and whatnot. So if you Google the variable, operating principles of the biosensor, it runs into hundreds of different principles, but anything is possible as long as it matches the desirable properties about which I'll talk, in a while. Then the kind of principle that you want to use could be an electrochemical principle, or what is called as amperometric, potentiometric, or it could be, if it is an optical signal, I may try to measure the absorbance or the fluorescence, or what is called as a chemiluminescence, in which, there will be illumination coming out of it, wherein the light can be measured, and so on and so forth, right? So these are the four very essential components of a biosensor. Hope you are all with me and able to get a feel of what will a biosensor contain: an analyte, a biorecognition element, then what's the change that is happening because of that, and then you have any of these, measurement techniques or measurement assays or procedures to have the information meaningfully converted into an information which is analogous to what you're trying to measure. So that becomes the philosophy of a biosensor, right? As simple as this. But this is the most important thing. Why? Because this is where the interface happens between the analyte and the bioreceptor, right? See, if you have the best of the best things here, but if this is very poor, so obviously your yield strength will be very poor and you will not have the best of the biosensor, right? So if you look at any of the research papers, they always look at these kind of an interaction and they say, I use some kind of a, polymer here. So that will interact with this glucose better. So that will give a better SNR. That could be one paper. Or somebody may say, I'll use the golden nanowires as my bioreceptor to detect the glucose in, say, the sweat or the tear signals, and I'm getting this response and so on and so forth. So the world over, they concentrate on what are the new kinds of novel interactions that you can develop between the analyte and the bioreceptor, so that you'll have a very meaningful description of the particular analyte you are trying to measure. These are all very well established. Transducer sensors are there, since ages. And same as your electronics and interface circuits. So and even this could be same for all the measurement. So people should concentrate on this. There is one more point to be noticed here. Remember, in addition to the analytes being small molecules, the bioreceptor also are very small molecules, right? So it's very important to do what is called as immobilize the bioreceptor. Hope my point is clear. For example, in the test strip that I was showing in the previous strip, that test strip already has the glucose oxidase as an enzyme. That enzyme is a bioreceptor. So now that enzyme should be fixed to a particular place so that the stability of the whole purpose will increase. For example, if I build a building, so I'll make the foundation very strong. If the foundation itself moves, the whole building moves, right? So there is no point in making such thing. So applying the same analogy to this particular thing. So this is the background on which you have fixed a bioreceptor on which the analyte is going to fix. And another beautiful reason why you have to do this is these analytes can change their properties or change their shape and so on and so forth. That was the biggest problem in detecting the coronavirus initially. They change themselves, they manipulate themselves. When that is the case, if your bioreceptor base is also unstable, so what is it you will end up with? You will end up with a very, very noisy situation. We don't want that to happen, right? So for very good detection to happen, it's very important that my bioreceptor is very stable, meaning they should be in an immobilized state. Immobilized means they can't move around, on the strip, so that I'll have a very good, stability. Hope you got the point that the bioreceptor should be very, very immobilized and should be very stable so that I can have a very meaningful interaction between the analyte and the bioreceptor. Now, to immobilize the bioreceptors or the biomolecules on a transducer surface, it affects the so-called biosensor stability and even the performance of the particular biosensor. Here it is. When the analyte goes to the restriction element, so the bioreceptor here should be very, very stable, right? So this is what is called as biomolecule immobilization, or it is immobilization of the bioreceptor which is working as a biomolecule, right? Or a biomolecule working as a bioreceptor, that should be immobilized. That should be very, very stable on the substrate of the transducer, right? So there are 5 different techniques that people use, what is called as the adsorption, or what is called as covalent bonding, or even what is called as cross-linking, or even entrapment, or what is called as microencapsulation. So using one of these 5 techniques, the scientist will ensure that on the matrix, the biomolecule, is immobilized like this. So whether you do the adsorption like this, or whether you can have a covalent bonding between the analyte and the bioreceptor, or the cross-linking of the various agents, or it could be an entrapment like this, or it could be microencapsulation like this. Ultimately, what you see in a different color here, that dark blue color is your bioreceptor, and what you see as a red background is your transducer surface. So we see that they are entrapped there, or they are covalently bonded there, or there is a cross-linking there. And once you have this very stable substrate in which the bioreceptor is in an immobilized state on the transducer surface, so your chances of good sensor performance is but obvious. Why? Because my ground is very stable. All of us know electrical circuits. The first thing you have to concentrate when you make an electrical circuit is a ground point, right? If you don't have a stable ground, what else can be stable in a given circuit? You tell me. Nothing could be very stable, right? So if you are a good electronics engineer, you will ensure a very, very good stable, ground for that matter, or zero potential point or a common connection point. If that is stable, the rest is stable. If that is unstable, the whole thing becomes unstable. So applying the same analogy to my, bio sensor to the bioreceptor, I need a very stable substrate with the bioreceptor permanently, adequately immobilized on the transducer surface to make the journey very, very simple, right? Hope it's clear. Now, these bioreceptors, as I told you, they play a very critical role in the whole philosophy of the bioreceptor or the biosensor. So if you have the best bioreceptor, the best biochemical reaction, you will have the best biosensor, right? So what are the different forms of, bioreceptor that people have encased? It could be what is called as antibody and antigen interactions. So there could be an antibody present on my substrate. So then my antigen is an analyte. So there is some interaction and I have the bioreception happening, or it could be the other way also. Right? Or my bioreceptor could be a protein which will interact with another protein to give me a biochemical reaction. So that can be encased to build my biosensor. Or it could be interactions between one nucleic acid and another nucleic acid. Or it could be enzyme-enzyme interaction. Or it would be cellular interactions. Or it could be interactions with what are called as a synthetic bioreceptor, or even aptamers, which are single-strand DNA structures, and even peptides. And I have my biosensor. Hope the heading is very clear. I'm trying to list out the 5 most common forms of bioreceptor, right? So bioreceptor is where the analyte goes and sits. So I can encache the antibody-antigen interaction or any one of these, 6 particular thing to develop my biosensor, right? And this particular website here will tell you the 12 classical difference between an antigen and an antibody. So you can always take a, detailed reading about the difference between these two. But antigen is what is there in the thing that is a foreign element trying to attack the human body, and antibody is what the body produces to fight against the antigen, right? For example, the coronavirus is an antigen, and the hemoglobins that I produce in my blood becomes antibody. So there will be a fight between those two. So that can be encased as a bioreception technique to come out with a novel biosensor technique. Hope the meaning of bioreceptor and the possible interactions are very clear to you. And now, as I've been telling you for a couple of 5 minutes, for a couple of minutes, the choice of the biological recognition element is the most crucial decision while developing a novel biosensor design, right? So let me repeat, if you Google the kind of research that is happening, most of them will try to, come out with a new technique of detecting an analyte, and nothing with your interface, nothing with your transducer, and nothing with your electronics or interface, because they are all very standardized, right? So if you want to do research on this, so you have to really think on new different lines and try to come out with a different interaction technique between these two, right? So these are the 6 possible ways of making bioreceptor. Now to, hit on a nail, let me take a very relevant example of antibody and antigen interaction based biosensor, and nothing more than the biosensor that is used to detect COVID-19 or the coronavirus, right? This is the structure of a coronavirus. It has got what are called as spike proteins and membrane protein and another protein RNA here. Then it has got a lipid membrane and so on and so forth, right? So now what you have to understand is that whenever somebody is infected with the coronavirus, the body produces antibodies, to fight against the corona. And this particular antibody will bind specifically to the so-called spike proteins. These are the spike protein points wherein the antibody produced by the body will try to bond with that, and even with other antigens that are being present here to try to help the body eliminate the virus. So all of us will have that immune system or the body fighting mechanism in which antibodies are like my soldiers. And antigens are like my enemies, when the enemies like the coronavirus attack my body soldiers will, come alive, and the body produces antibodies that try to fight with this. And how do they fight? They first try to bind to the spike proteins or even other antigens, right? So that is the philosophy. That is a phenomenon that happens. Why it happens, we don't know. That happens. Only science has to explain. But when that happens, we can harness that particular binding to develop a test which is based on this antibody and antigen interaction, and then tell whether somebody is infected with corona or not, or what is the extent to which somebody is being infected can always be told, right? I hope I made the point very clear here. So the classic example of a biosensor or any sensing technique that is based on antibody and antigen interaction is the corona detection, in which the body's antibody will react or will have kind of a binding with the antigen of the particular coronavirus or even the spike protein. So that can be used. Now, there are two ways of doing the test for corona. The first test is what is called as a diagnostic test, and the second is what is called as an antibody test. What does the diagnostic test do? It shows that somebody has coronavirus. It's only detecting. It's not trying to quantify. It's not trying to measure. The so-called PCR machines, which are called as polymerase chain reaction machines, they do what is called as molecular test. They try to detect the virus genetic material. So coronavirus is supposed to have a particular gene, and so this PCR machine will try to amplify the gene, DNA structures of the genetic material of the coronavirus, and then after the given time, it will tell that whether this gene is there or not. So that becomes the PCR machine that will detect the presence of the coronavirus. The second technique is what is called as an antigen test, which will tell that this particular protein is present on the surface of the virus, and this is coronavirus, so this protein has to be present, otherwise the result could be negative. Right? So the first diagnostic test is what I'm trying to talk about, will just detect the gene of the coronavirus, or it will detect the specific proteins that I showed you in the previous slide to tell about the presence of this particular coronavirus. Now, this is a very popular test, what is called as the antibody test, which will look for the antibodies produced by the body or your immune system, which is in response to the threat of the coronavirus to fight the infections. I told you in the very beginning that antibodies are my soldiers which will fight against the coronavirus, and you can have a test to check whether your body has IgM and IgG as the antibodies. So if your body has it at all, so that means if my blood sample shows IgM and IgG, it means that I'm corona infected, and my body is producing IgM and IgG, to fight against the corona infection. But one very unfortunate thing about the whole philosophy is that it takes several days or weeks to develop after an infection. So if I'm infected with corona, it would take a week or 2 weeks for my immune system to develop, IgM and IgG, and it may be too late to have myself detected with that, and all these problems. And another worst thing is that it will continue to stay in the bloodstream even for, a few weeks after the recovery. So this is the reason where we tell people, that he was alright and there was no symptoms and suddenly he developed something. I mean, these are all the science behind it, about which, we can't help it. And this picture shows that we're all confused about this, and I wish the confusion will clarify in the coming months, and we pray for the same. And in the case of the SARS-CoV-2 virus, the IgM antibody response peaks around 1 or 2 weeks after the infection, and followed by the IgG antibody peak after 3 weeks or so. And these are the structures of the IgM and IgG, hemoglobins produced by the body, which are the antibodies. And unfortunate that they start responding little late, not as soon as the incubation period happens, right? So if this is where the coronavirus gets into my body, so it will, around incubate for around 15 days or so. Then during the first week, if I'm tested, it will show the presence of the antibody called as IgM. This is happening because my body has produced IgM that is trying to interact with the antigen of the coronavirus, and the laboratory test will tell that I have the IgM being developed. My body develops IgM because it is fighting with coronavirus. Or after some another 1 or 2 weeks, if I'm tested both for IgM and IgG, my body is still finding for it, and after the 35th day, this IgM will subside, the body will stop producing IgM, and it will be only IgG which will continue to stay, right? So this is where the virus is detectable, and this is where we have fever and symptoms, and this is the IgM antibody, and this is the IgG antibody that the immune system of the human being will start fighting after some time or so. I think this is a very striking example and a very relevant example to tell you how biosensing technologies can be explored in the form of the interaction that happens between the antibody of the human body and the antigen of the coronavirus, and they do interface, they do bind to each other, and that can be encased to know that somebody is infected with coronavirus or not, right? Hope the point is driven. When it comes to the antibody test, how do I test the antibody? They detect the antibodies in the blood, like what I showed you in the previous slide. The detection of the IgM and the IgG should be done using what are called as the antibody test, and they can be detected using different type of tests, what is called as ELISA, which is called as enzyme-based immunoabsorbent assay. That looks like this. So there is a tray, and there is a whole lot of procedure. I'm not going to the details of that in the interest of time. But that's one test to know that I do have the antibodies in my blood sample. Or it could be what is called a CIA, which is chemiluminescent immunoassay, which is a test like this, and it could be point of care test based on the lateral flow technology. This is how the typical the blood sugar test or the pregnancy test strip or the urine glucose test strip happens. So we have a test strip which is what is called as a lateral flow technology, in which you put the drop here and it flows, and based on the kind of color change that will happen, you can know whether an antibody is present or not, right? So far what I have done, friends, is that I try to speak about the small molecules which are very important to be detected, and then we define biosensor and the components of the different biosensors. And the most important critical element is the interaction that happens between the analyte you're trying to measure and the biorecognition element. So you choose it to be the best, the whole thing will be very best. And based on the kind of interaction that happens between the target you're trying to measure and the bioreceptor that is being already present, we can have 6 different type of interactions. And the very popular example I took are the antibody-antigen interaction, using which you can detect the presence of a coronavirus in the human serum, right? So that's what we have done so far today. If there are no doubts, I'll continue. Probably we can always take the questions at the end of the presentation. Now, having said this, what are the desirable properties of biosensors? Right? So let me talk about the desirable properties of the biosensor. The first and foremost important thing is a high degree of specificity, or what is called as selectivity, right? So if you look at this particular picture, you have somebody fishing, and the pond has all kinds of fishes, but now he is supposed to, take out a particular type of fish and not every type of fish, right? So this is a fish I want to catch, and similarly, this is a particular analyte I want to pick. My testing technique should not pick something else undesirably. So that's what I'm trying to do here, right? For example, if you look at the tear that we produce when we cry, or the tear fluid that is present on the eyelids or the retina, it has got these 8 to 10 different components. This is for 1 unit of tear sample. It has got Na+, it has got K+, it has got chlorine minus, it has got magnesium plus, it has got calcium plus, then it has got bicarbonate, HCO3 minus, and then it has got urea, it has got ascorbate, it has got lactase, glucose, and it also has a protein and what not. A simple drop of tear has all these chemical compounds in that, and it's because of the presence of these, salts in the tear that it tastes salty. If you taste a drop of tear, it is obviously salty because of the rich ions that it has, right? Now let me say I want to develop a biosensor in which I want to measure what is the glucose in my body. So people have researched also to measure glucose in the tear, or glucose in the sweat, or glucose in the saliva, then try to correlate that with the glucose in the blood. So that's a different field study altogether. What I'm trying to drive here is that the sample can have a whole lot of compounds. If I want to detect this, I should have a biosensor that is responsive only to this and not the rest of it, right? So if there is a sensor that senses Na plus also, Ca2 plus also, and urea also, it is a stupid thing that we can have, right? You can't use it at all. So specificity or selectivity becomes a very, very important characteristic of what is called as a biosensor. It should be able to pick what it does and ignore other components of the thing. The second important requirement is what is called as a good stability to operating conditions. Even if the temperature changes or the pH changes or the ionic strength changes, etc., my biosensor tip should not really bother about all these changes. It is said to be having a good stability, right? Remember, if I make a biosensor for pH, I don't have control over the medium of pH that I'm trying to measure, right? So it should not vary itself because the medium is different, right? So that's what it means, that I should have a very, very good stability under all the wide range of operating conditions. That becomes the second requirement, right? And it should not unnecessarily, contaminate the whole sample. So that's again undesirable. And you should have good sensitivity. Who doesn't have good sensitivity? Remember, sensitivity is a change in the output to the change in the input. It's the ratio of the effect to the cause. For a given cause, if the effect is more, that is fantastic. And my life becomes very easy if you have got good value of sensitivity. And the fifth and foremost important requirement of a biosensor is what is called as a long shelf life, at least 6 months to 1 year or even beyond. Right? So if you have a biosensor to measure your blood glucose at your home, and you will also buy strips, which are a little expensive. Maybe for 30 strips, you may spend around 1,000 rupees. And if you say use it within 1 month, it's only to save money that you have to use all of them in 1 month. That is not correct at all. So if I can store them for 1 or say 6 months to 1 year, without themselves getting degraded in performance, that is highly desirable. That becomes cost effective or economical. So that becomes the fifth requirement. And the sixth requirement is the possibility of chemical modification or immobilization. I told you in the beginning that it's very important to immobilize the bioreceptor on the substrate of the transducer. So they should be able to do that. Suppose if I have the best of the biosensor with, let me say, very good specificity or very good stability, but if we can't, chemically modify that, or if we cannot immobilize that on the substrate, that becomes again useless, right? And then the retention of biological activity in immobilized state, right? So the bioreceptor is immobilized. So now there is a biochemical actioning that is happening. Even that should be retained there. Remember, all these things happen at the small molecule scale, which is in nano and even femto kind of a scale that, these are happening. Invisible even to the best of the microscopes, right? So in that case, mobility is the obvious thing. So the more immobilized it is, not only the substrate, but even the chemical reaction that happens, if it can be, captured there, you have the best sensor. These are desirable properties. Desirable or only desirable. You may not have the sensor with all the, 7 being possible, but at least most of them, if you have low, you have the best biosensor being fabricated, right? Yeah. So we'll move on. Now, if you look at the way the biosensors are classified, so that is little mind-blowing. And it's very difficult to classify biosensor. But let me take, 2 to 3 different approaches. One could be, the biosensors could be classified based on what is the biological element that you are trying to use, or what is the biorecognition element you are trying to use, right? So it could be, you can call the biosensor as antibody-based, or DNA-based, enzyme-based, or biomimetic-based, or phage-based. You know what a phage is? Phage is a special kind of a virus that can infect bacteria. I see, nature is amazing. Nature is awesome. So you can even make biosensor based on phage and based on the transduction method. Remember, after the biochemical reaction, there is always some physiological output that should be again transduced, right? So I require a kind of a transduction method. So it could be best, it could be called as an optical sensor. If I use some kind of a fiber optic principle, or what is called as a surface plasma resonance, or the Raman and FTIR spectroscopy, or any other technique that is based on optics, you can call them as optical biosensor. Or it could be the electrochemical biosensor, in which you have an anode, you have a cathode, and your biosample going there, then making some kind of a chemical reaction, or the loss and gain of electrons called as a redox reaction. So that becomes, a biosensor. And you can have the potentiometric sensor, or the amperometric sensor. Potentiometric sensor is one in which I measure the voltage between the 2 electrodes. Amperometric, I measure the current between the 2 electrodes. And the conductometric, I measure the conductivity. Impedance, I may be able to even measure the resistance between the 2 anode and the cathode, ultimately to quantify what is the kind of, reaction that has happened. Or it could be even mass-based biosensors, in which, because my analyte is going and sitting on the bioreceptor, the mass may change. The mass, please don't think it's heavy. It could be even nanograms or even less than that. But there are very sensitive devices to even detect those changes in the masses. Could be based on the magnetoelectric properties, or it could be based on the piezoelectric properties, what is called as a quartz crystal microbalance, or QCM, or the surface acoustic wave kind of a thing. Using which I can detect the mass, right? So ultimately, if you root back to this, so based on any of this, you are able to try to correlate what is the final output that you got back to the concentration of the analyte. And we have witnessed huge number of different principles that are being adopted to develop all these biosensors, right? I'm not talking much details about this classification here, but just to be in the line of totality, I have just put one slide here to tell about how biosensors are classified in the field. And so it should not be confusing, but they're all somehow related to each other. But based on the principle, it could be optical, electrochemical, or it could be mass-based, or based on the element, it could be any one of this particular element, right? Hope the point is clear to you. Now with this background, so let me take a case study on the glucose biosensor and its growth. You know what is glucose, right? So that is the simplest of the carbohydrates, which is called as a monosaccharide. That means it has got only one sugar. When it has got multiple sugars, that is called as polysaccharides. So glucose is a monosaccharide, which is the simplest of the carbohydrates. And along with the fat, glucose is one of the body's preferred sources of fuel in the form of carbohydrates. That's the reason we'll have a cup of tea with sugar, etc. So that will give a kick in your energy and you can go on with your life, right? So fat and carbohydrates are very essential for our, existence, because body is a chemical factory for that matter, right? With infinite number of chemical reactions happening in the body, right? So cells are active, birth to death. They are all, factories with no lockdown, with no shutdown, and so on and so forth. On the lighter side, anyway. We know what happens when the sugar becomes excess, or the pancreas is unable to produce the insulin that is required. So body does nothing else other than pumping this extra sugar into the blood. So the blood glucose goes up and the person becomes diabetic. And I also know the problems of diabetic being one, so it's very difficult. And if you look at the world situation, in 2015, 416 million of the world population was diabetic infected. And by the year 2040, it may even go to 642 million. So which means 54% of the world's population will be diabetic. So diabetes is one of the most common problem. They say it is not a disease, it's a change in the lifestyle. That's a philosophy to make the life comfortable. But I know how difficult it is to deal with diabetes.
Give energy to us, sir. Give that energy to us. Okay, sir. Okay.
Yes, sir. So therefore, I'm taking this example of diabetes, which is very, a popular example to be taken, right? Now to talk about, the detection of blood glucose, let me take the example of, Professor Leland C. Clark, who developed the first biosensor, which is used to measure the so-called glucose, right? He was there from 1980 to 2005. Somewhere in 1962 or so, he developed the first commercial glucose biosensor, which typically looks like this. This is kind of an electrochemical sensor with an anode and a cathode, a platinum cathode and a silver anode. And if you look at this particular part of the picture, you have what is called an enzyme layer containing glucose oxidase. So now please understand, my glucose oxidase is a bioreceptor I have been talking about, right? So that particular bioreceptor or the glucose oxidase should be immobilized on this particular membrane. It should not become movable, right? So that my detection becomes very easy. And you have what is called as an oxygen permeable membrane here, because the whole reaction requires oxygen for its operation. And then the rest of it is very simple. So therefore, the glucose what you are trying to measure, for example, I can take this electrode and dip it in a sample whose glucose I want to monitor, right? When you do that, so glucose plus oxygen in the presence of the glucose oxidase gives what is called as a gluconic acid and even the H2O2 or hydrogen peroxide. So this glucose oxidase is present on the surface of the electrode. So what is input is the glucose, and glucose oxidase is present, and the product is H2O2 as well as gluconic acid, but it consumes oxygen for its operation, right? So this whole device will not work if the oxygen present around the environment is very, very less. Anyway, so that's a different philosophy. So that was the birth of the first glucose biosensor. You may be thinking, why is that study taking back us to 1960s when we have such modern biosensors? Believe me, trust me, even today, the most advanced biosensors are based on the first principle that was developed by Professor Leland C. Clark. So that's the reason why he is called as, father of biosensors, even remembered today, even after his demise in 2005. I often tell, great people are the ones who are remembered even after their death, right? So he was one such great scientist who gave the world the so-called glucose biosensor, right? So again, the same thing is repeated, and we call them as the first generation glucose biosensors, in which the glucose and oxygen in the presence of GOX, the glucose oxidase, will give us a gluconic acid and even a hydrogen peroxide, right? Now, how do I know the glucose concentration? So there are two ways of doing that. You can either measure the concentration of O2, reduce concentration of O2 because O2 is being consumed, or you can find out what is the rate at which H2O2 is being produced, right? Remember the equation. On the LHS, it is consuming oxygen to produce H2O2 and gluconic acid. So you can know what is the glucose present in the given sample or the analyte based on how much of O2 is consumed or how much of H2O has been produced. So that requires another instrumentation technique. This is what I was trying to tell you. So this is a reaction that has happened on the bioreceptor or a biochemical reaction. Now we should use a transduction technique to encash this chemical reaction and either measure O2 or measure H2O2, then calibrate your biosensor to read in terms of the glucose that is being consumed. But it was a very good old technique, but not very popular even today, but still the basic principle is used. So what happened in later is that it had a demerit that it was strongly dependent on the ambient oxygen. If it was used in an environment where there is a deficiency of oxygen, the response was very nonlinear and poor. And even the other electroactive compounds in the blood were trying to do some interference reaction, and that was indesirable, right? So, I mean, this is how the first generation of glucose biosensor works, and these are the two disadvantages. What happened later was that, so other scientists extended the work of Clark, and they used another additional electrode to get the electrons recognized. So they stopped measuring that consumption of O2 or the release of H2O2, hydrogen peroxide, and they started converting that into an electron, and they started counting the electron, which is proportional to the number of glucose molecules present, right? So A to B is what Clark did, in which glucose with O2 gave you gluconic acid plus H2O2. But now the addition of another electrode, which was maintained, I think, at 0.6 volt or 0.2 volt, was able to, again break out the things, and they were able to get the 2H ions or the oxygen molecules again, and again 2E minus, right? So they were able to again get back the oxygen. This was the product of the research that people did, and it started liberating the electrons which were counted. So the Clark electrodes was improved by other scientists, and it became all the more easy to measure the electrons which were proportional to the glucose molecules that are being present, right? Then, humans are always greedy and they wanted something better. So they came to the second generation of glucose biosensors, which uses, what are called as mediators. Mediators are, very small soluble redox active molecules, like the ferrocene derivatives. They can quickly undergo both, reversible redox reactions. So that means they can quickly oxidize as well as reduce. So that means they can take an electron or release an electron very quickly. So therefore, between the membrane and the actual electrode, so they started using, this particular glucose oxidase is present here. So then they use this Fe, which is now the glucose biosensor. So they started shuttling the electron from the center of the glucose oxidase to the electrode here. So they speed it up. Mediator is like having some kind of a catalyst fellow in between who try to speed up the whole thing. And so they shuttle the electrons very fast. So doing this second generation in which what are called as the mediators were used to shuttle the electron from the glucose oxidase back to the electrode. They did some advantages like the specificity improved, the reliability improved, and based on the 2G generation of glucose biosensor, the first commercial device was developed in the year 1987. And also it alleviated the influence of the interfering molecules, which was there in the first generation. And also there is no more dependence on the oxygen for glucose monitoring because we're trying to measure directly the electrons that are being produced, right? So that led to the commercialization of whole devices of the glucose biosensors for glucose detection starting from the year 1987. So then onwards, more than 3 to 4 manufacturers started building these sensors, like, LifeScan or the Roche Diagnostics, which gives the AccuCheck that even I have at home. Then Bayer Diagnostic as a glucometer called as a Light XL. Then TerraSense Freestyle, and there are so many sensors available. So these are the typical specifications which give you what is the sample size, what is the test time, and what is the temperature range, and can you download the data and so on and so forth. So people started making commercial biosensors, glucose biosensors starting from 1987. But as I told you, we always wanted to improve things. So then they started thinking of nanomaterials, right? And they found that, the research found that the nanomaterials, are very, very good materials in immobilizing the glucose oxidase. I have been telling you time and again that it's very important to immobilize the glucose oxidase, which will give a large surface area, And because of you're using nanotechnology, when you have a nanomaterial in a very thin core, the large surface area compared to the thickness is very large, and that will increase the electron transfer capability, and even sensitivity it will improve. The response time has been improved. So the people started using the biomaterials in various forms and shapes, along with the 2G generation biosensors, and that gave huge number of advantages, right? So the second generation of glucose biosensor that still use mediators have been built in the world today, and they use nanomaterials, they can use the carbon nano onions, or they can use graphene, or they can use the nanoparticles, or they can use the carbon nanofibers, or the carbon nanotubes, or the quantum dots, or the metallic nanoparticles, or metallic nanospheres and things like that. So they have been extensively used. Probably I'll take 2 examples toward the end of my talk to impress you upon the importance of nanomaterials in the developing the novel biosensors. But mediators are always problems, right? So the way mediators face problems to us, even here, some of the problems remain with the mediators that here and there they produce irreproducible results, and even they started becoming biotoxic. So that was some kind of a disadvantage that people found, even after exploring the application of nanomaterials to modernize the so-called 2G glucose biosensors. So what will the third generation glucose biosensor do is, there is always an intrinsic barrier to electronic flow because of what is called as the globular structure of GOX. GOX, or the glucose oxidase, has got a very complex structure, the molecular structure, and it's always a big challenge to take out the electron from there, and that's the reason why people started using the mediator. And so they wanted to do away with the mediator. Now people are talking about what is called the direct electron transfer, right from the center of this particular enzyme, where that reaction is happening, to the electrode directly. And that was very difficult until people started, developing and using what are called as the gold nanowires, or the nanoparticles, or the CNTs, which are of very, very, very nanoscale. So they can reach the center of the particular glucose oxidase and directly get the electron taken out from there. So things started becoming better. So therefore, the 3D or the third generation of glucose biosensors are nothing but the ones that will not use the mediator. Instead, they will try to take out the electron that is being produced because of the reaction directly into the electrode, so that will speed up the whole thing. And highly sensitive and selective third generation biosensors have been developed. Like for example, these particular authors from Singapore have developed what is called as a nanoporous tin oxide and GOX modified glassy carbon electrode, and they were able to achieve a very fast response of around 5 seconds and a very high sensitivity of 9.9 microampere. That's quite huge, for 1 millimole for a given centimeter square area. So they have been able to achieve very high sensitivity, right? This particular picture will summarize what I spoke to you for the last 15-20 minutes to compare the 3 generation of glucose biosensors. The first one, the electrons are transferred using, they were trying to measure the consumption of O2 or the production of H2O2, which was very tedious in the glass electrode. So then they introduced an electrode and they tried to measure, but they were not able to get them at a very fast rate. They were very, very slow in operation, and the sensitivity also was very less. So in the second generation, people started using mediator, which can quickly lose an electron and gain an electron, in the process of which it was able to transfer the electron from the place where it is being produced to the electrode. And that was tedious, and because mediators also had their own role to play, disadvantages to contribute, so people did away with the mediators. And in the third generation glucose biosensors, people have been successfully transferring the electron directly from the center of the enzyme or the glucose oxidase to the electrode, and they're very fast today. So the sensor that we are going to get hereafter are based on the DTE, or the direct electron transfer, in which the sensitivity is good, the accuracy is good, the response is also very, very good. So these are the ones that will satisfy at least most of the desirable properties of biosensor, what I was trying to list earlier, right? Yeah, so this reflects the simplification and enhancement of the transduction pathway. 1G to 3G to 3G, it shows how people simplified and enhanced the transduction pathway to make the electron reach the electrode as fast as possible. Now, I just mentioned that the nanomaterials have played a very big role in the development of the so-called biosensor. So let me now talk about what kind of nanomaterials can be used or how do they impact on the performance of the particular biosensors, right? And before I go to the details, I'll just define a nanomaterial. All of us know that. So if you look at a tennis ball, so that will have a diameter of 10 centimeter, a small dot will have 1 millimeter, or the human cell or any cell for that matter will have a approximate of 0.01 mm, or a bacteria will have 0.001 millimeter, the virus will have 100 nanometer, and a molecule will have 1 nanometer, and an atom will have 1 angstrom. So nanomaterials are the materials whose dimensions are in the range of 1 nanometer to 100 nanometer. We call any material that can be produced, manufactured, or prepared in a scale called as nano, we call them as nanomaterials, right? The beautiful advantage of nanomaterials is that they can be manufactured and used at a nanoscale, already being told, and they exhibit very novel characteristics that are not present in their bulk property. That's the beauty of nanomaterials. See, if you take a piece of charcoal, that is nothing but carbon. It may not have any attractive property at all. But if you can make the carbon to take the shape of a carbon nanotube, it will have wonderful different properties. Therefore, that's the advantage of nanomaterial, like increased strength, the chemical reactivity may be different, or even the conductivity may change, and so on and so forth. So just take a look at this particular picture. If this is a bulk band structure of a given material, and this is the band gap, so instead of having a bulk material like this, if you can make a quantum dot of this particular size, you see the increase in the energy band gap. And if the size of the quantum dot further reduces and the band gap further increases, and so the band gap is inversely related to the size of the quantum dot. So that's the point I'm trying to drive here, is that you can play with the size of the nanomaterial or the nanoparticle, and you can easily play with the electrical properties, mechanical properties, chemical properties, and whatnot. So therefore, there is a outburst in the so-called nanotechnology used in almost everything that is being possible. See, for example, if you go to Nandini, you buy something called as a Good Life, and they say this can be used for 6 months. How is it possible? The same milk, what's the treatment they're trying to do? They just change the size of the particles and pack it, and it becomes more preservative for say 3 months, right? In fact, I was attending one talk wherein one scientist told that they are planning to bring to the market the packaged curd rice that will have a shelf life of 8 months. So that is amazing. No chemicals added. That is possible because they play with the size of the constituents of the so-called curd rice, and it becomes preservable for 6 to 8 months. That's one standing out example I often remember to highlight the importance of the so-called nanotechnology. And once you go to the nanoscale, you can, the materials will possess very different physical properties, such as particle aggregation, or the photoemission properties will come into play, which were not there when they were bulk. And even the electrical and heat conductivity will be totally different from what they were not having when they were bulk, or even the chemical properties like the catalytic activities will totally change just because they're in a nanoscale, right? Yeah, so there are all the differences. And so much attention it has attracted in biomedical sciences also for the cases of biomolecule detection or sensing applications, and even gene delivery and clinical diagnostics. And more details of this can be found from this particular paper. But the point I'm trying to drive here is that after developing the so-called 3G biosensors also, people started exploring the different kinds of bio and nanomaterials in different forms, like the dots or the CNTs or the nanofibers or the nanoonions that can play a role in improving the performance of the biosensors. And whenever I talk about a bioparticle, there are 4 aspects of a nanoparticle. What is its shape? What is the material that is made use of? And what is the size of it? Or what is the surface? So these are the 4 important points that we have to talk about a nanoparticle, are the 4 characteristic features of a nanoparticle. The shape could be a star-shaped or a cube, or it could be helix, it could be triangular, it could be a rod, or it could be a sphere. And the material I could use could be an hydrogel or a metallic nanoparticle, or it could be a polymer, or it could be a dendrimer, or there could be derivatives of graphenes, or it could be micelle, or it could be DNA, RNA strand structure, or it could be graphene biomolecule conjugates, or even it could be proteins like this, and carbon nanotubes and whatnot. And the size should be, could be anything from 1 nanometer to 100 nanometer. and the surface could be hydrophilic or hydrophobic. It may be reluctant to take water, it may be happy to take water, and the surface change, could be within the surface charge could be some, delta plus or minus millivolt, and it could belong to different functional groups. Or the targeting ligand could be an antibody or a peptide, an aptamer, and so on and so forth. So if you try to make permutation and combination of all this, just imagine the number of combinations you are going to get. But it does not mean that you can go and start doing all of them. So that's what is research all about, but it's not again by trial and error. So there should be some scientific reason why you want to, attach something, or you want to come out with a different technique, so that you'll have a very meaningful measurement. So this particular slide gives the different aspects of a nanoparticle that you need to look into whenever you want to make a biosensor or anything for that matter. And now when I talk about nanomaterials in the case of biosensing, so people have used carbon nanotubes to make biosensors, and they improved the enzyme loading and the aspect ratios increased, and it became easy to functionalize them, and the electrical communication became better, and they used even nanoparticles, and that again gave so much of advantages. And they used quantum dots also, that will give the property of the fluorescence or quantum confinement of the charge carriers. Confinement is very important, again, especially because everything is nano and micro, they should not run away from the whole thing. So it should be possible to confine them. That is possible in quantum dots, and even the size and tunable energy. I just showed you a picture before. When you work with quantum dots, by varying the size of it, you can control the energy band of that. And even people have used nanowires, which are very versatile. They will have very good electrical and sensing properties for biochemical sensing. And the charge conductor is always better in nanowires, and even nanorods have been used, and so on and so forth. So this particular slide shows the 5 different kind of, nanomaterials or the nanostructures people have used to make the biosensors for novel biosensing of things. But given the time and the interest and your attention span, it's impossible for me to talk about all of them. So I've chosen 2 case studies here, or 2 examples here, one based on quantum dot, developed by a few scientists, and they have been successful to measure cholesterol content, and people also have fabricated a device using nanowires to measure the DNA as the target DNA. So this is the first example I'm trying to give, which is for cholesterol detection, and they could achieve a very high sensitivity of around 97 millivolt per 1 decade change in the cholesterol concentration. It is based on the indium nitrate and indium gallium nitrate quantum dot, which again uses an electrochemical reaction, meaning that it should have an anode, cathode, and redox reaction that are being possible. It was published in Sciences magazine in 2013. You can always take a detailed look at this particular paper if you are interested. We know what is cholesterol. Cholesterol has both bad and good cholesterol for us. So the good cholesterol could be on the higher side, and the bad cholesterol should be on the lower side. Doctor will know better of it. But the detection of cholesterol, which can relate, which is related to the cardiac problems, is very, very important. So in addition to the chromatographic techniques of knowing what is the cholesterol level in a blood sample, we would love to have a cholesterol sensor right at home, using which I can know how good I am, how good, is my health, right? And they used indium nitrate, which is called as a 3,5 group of semiconductor, preferably because it will have very high electron concentration near the surface. You remember I was just trying to show what is the, about the charge confinement, or what is the surface charge on the, on the surface. And indium nitrate has this particular advantage that the electron concentration is very high near the surface, and it has got very good chemical stability, and also it is high sensitivity to changes in the charges in the environment. It's very sensitive, so therefore the sensitivity of this device has been excellent, to the tune of 97 millivolt per decade. And this is the way they fabricated this particular device. They just took sapphire that was coated with gallium nitrate, and again coated with indium gallium nitrate compound. So then they were able to, use a suitable screen printing technique to make these dots. So then the remaining taken was taken out, and again, as it was again coated with CHOX and Nephlon to have good stability and things like that. And then that became the reference electrode, and this is your particular sensor that were dipped in the cholesterol solution, and they measured the voltage being produced at different cholesterol concentration levels using the Keithley 2400, source meter. and here are the results that they produce. And before I go to the result, this is the basic, reaction that happens. Don't worry if you don't get a feel of the whole thing, but I have put this equation just to emphasize that most of the biosensors are based on what is called as that biochemical reaction that happens between the analyte and the bioreceptor. So the cholesterol reacts with O2 in the presence of CHOX or cholesterol oxide to produce this ketosteroid and H2O2, which is again isomerized to have this, and ultimately it will develop a voltage as a function of the cholesterol content, right? And this electrochemical reaction is responsible for the charge transfer near the surface of the working and reference electrodes to produce an electrochemical cell voltage, right? So as shown in this particular figure, so the electrochemical voltage that is being produced between these two electrodes was always a function of the cholesterol content, as I'll show it in the next figure. One interesting thing that these authors have done is they have developed the biosensor both using the thin film of indium nitrate and also indium nitrate quantum dot, just to compare the two and highlight the advantages of making things to the nano level rather than a thin film level, right? So in the thin film level, for a log concentration from -6 to 3, they were able to get around 480 millivolt of EMF, but for the same concentration level, they were able to almost double the sensitivity when they made the device as a quantum dot sensor. And of course, they have done huge number of experiments and they have done some linear fitting also. So don't worry about the whole details of this particular graph if you're not so interested. But just get a feel of the whole device that just by changing the device from thin film to the quantum dot based sensor, they almost doubled the sensitivity of the device. So thanks to the application of nanotechnology, in which things become more sensitive with various advantages. And sensitivity is a very desirable property. The higher it is, the better it is, because the instrumentation becomes easy, the analysis becomes easy, or handling the signal becomes easy, and so on and so forth, right? And they also looked at the stability of that. For example, the thin film based sensor, kind of started drooping. This is the EMF versus as a function of time for a given fixed concentration. Let me say it was subjected to some X level of cholesterol concentration. So this particular thin film based sensor, maybe after 80 seconds or so, there was a small drip in the voltage, or there was a small drop in the voltage, but whereas the quantum dot based biosensor was relatively stable and even at a higher value. Look at this, this produces around 422, this produces around 900, which is almost more than twice of that EMF in the quantum dot. And not only that, it is more stable, the plus or minus variations of the final value is very less in this compared to this. So these are the result to just to impress upon the idea that biosensor based on quantum dots have proved to be very excellent resources to detect cholesterol. They even found the repeatability of the instrument. So that is, they measured the cholesterol, they kept the cholesterol constant and they repeatedly measured that, on day 1, day 2 and up to 10 days or so. As you can see here, the EMF produced is almost same. So they gave excellent repeatability or reproducibility, and the device is very, reliable. And the changes as a function of temperature also are not very, very large. Because at 20 it is around 900, at 30 it's a little more than that, at 40 it is little more than that, and as you further increase the temperature, the EMF reduces. So there should be a reason in the science for that to happen also. So they can claim that the optimum temperature of this particular sensor is around 40 degrees centigrade. Don't use that beyond 40 degrees. So that's how, all devices will come out with some kind of a specification for that matter, right? So that's about this particular device, and people have been able to successfully make a measuring device called as a biosensor, which is based on the electrochemical operation, and they have done that. And the second example that I'll take is, a biosensor being fabricated using the top-down approach of nanofabrication. And people have been able to successfully, develop the 20 nanometer silicon nanowires for biosensing applications. And these are the authors. This is where the paper is available. And they were able to detect the DNA molecules. See, we always prefer top-down approach because that's what we can do. God is the best engineer who can do bottom-up approach. And I think for our own limitations, bottom-up is always very challenging. In fact, if you agree with me, the entire VLSI industry works preferably on the top-down approach because things are under your control and bottom-up is extremely difficult. So this is one example that is being given here. So this particular set of authors, they developed silicon nanowires on a silicon on insulator wafer. they used a particular technique called as electron beam lithography, and they used the plasma reactive ion etching, which is a part of a fabrication procedure of all these sensors, right? And upon hybridization with the target DNA what you were trying to detect, and the response was phenomenal. And they were able to measure drain current as a function of the DNA chain, or even the resistance as a function of the DNA chain. And I'll show the result at the end of this particular presentation. The response was quite good. And this is the nano, wire that they produced of silicon oxide. And so in width it was 20 nanometer and it was 30 nanometer in height, and up to 80% or so it had got a triangular kind of a shape, and they were very precisely fabricated, the design location of the particular device, and this is how the silicon nanowire looked like. This is one SEM image taken for the particular sensor. Now, how did they went about fabricating that kind of a nanowire based sensor is as follows. It's very detailed, but I'll very quickly try to explain so that you can get a feel of it. So the starting material was silicon on insulator wafer. So they cleaned the wafer, then they cut it to a size of 2 centimeter by 20 centimeter. So then that was coated with the photoresist coating, whose thickness was also measured appropriately using a suitable device. What is called a beta scope is a device that is used to measure the thickness of that. So then they used kind of a pattern like a template or a stencil, what we call it as, that was generated by using the Rate L3 quantum GDS2 editor. They were able to make these arrays or single lines of templates or the stencil cards, which was placed onto this. Then they exposed that to the beam focusing or beam current. After proper coordination system was adjusted, because they always wanted to get where it was required to be obtained. So then they adjusted the exposure parameters. I'm sure all of us have some knowledge of the photolithography. That's what I'm trying to explain here. And then the development process was again done. So after the development process, so they were left out with this, and then they'll have to take out the photoresist. Photoresist is always for use and throw kind of a purpose, and this is what they got. So they etched out the unused thing, and ultimately they were able to get a silicon nanowires like this. And this shows the EDX spectroscopy, which shows the elemental content and purity of metals. So it was 99% of the golden nanowire that they wanted to start with. And this is the high power microscopy infection that shows the pattern of the profile of the particular nanowire, and this shows the SEM profile and even the structure. And using the AFM, they were able to know the profile or the surface topography. So they were able to make silicon nanowires of the diameter of 20 micrometer, and they made a device like this. That's very interesting. So they had an inlet here and they had an outlet here where you can put the sample that you want to analyze. And they have a kind of a channel here called as a microfluidic channel, and on either side you have pads. This could become the plus and that could become the minus, or you can call one as a drain and one as a source, and as a fluid force based on the the DNA that you're trying to detect, the resistivity was different, which was being measured. So this is how it all looked like, the microfluidic channel that is being present here, and it had a drain and it had a source, and the plus voltage could be applied here, and other dimensions are visible to you. And this is where the microfluidic channel is there, to which the sample that was supposed to be measured was made to flow, and the conductivity of the nanowire changed as a function of that particular DNA target, and they were able to make some measurement. So this was during the process of development, in which the initial device had a very, very poor response like this. So then they modified the surface, and then they made a non-complementary control. They were trying to immobilize the target, the bioreceptor. Then after hybridization and all, things got better. And with this hybridization of 10 micrometer, they started getting a better response. Anyway, this is the initial response. What is of my interest is the next slide, in which as they increase the target DNA concentration, the R by R naught ratio, resistance ratio increased enormously, from somewhere around 15 to 25 to around 60 to 70, 75 and so on, quite linear response. So this was the example of a second biosensor that I spoke to you about, which is based on the employment of nanotechnology to make the so-called silicon nanowires based on the top-down approach, and they were able to detect the target DNA using this particular sensor, right? Now, if you look at, I spoke to you for more than an hour and a half about, this biosensor, the way you make, what are the components that the biosensors are made up of, or what are the detection principles, and what is that important, we have to look at it, and how did the nanomaterials, improve the whole response of the biosensor, all that we have discussed. But now if you look at the application of biosensors, somewhere in the beginning I told that they were mostly for the purpose of health industry or the disease detection. But once people started developing biosensors, they are enormously used for everything like the environmental monitoring, the soil quality monitoring, the food quality monitoring, the toxin of defense interest. In fact, in biological warfare, even as a biosensor to know whether a country has thrown some bioweapon and things like that. They're used for water quality management. They're used in prosthetic devices. They're used in drug discovery. Even in the pharmaceutical industry, to come out with new drugs, to know what is effective, what is not effective, biosensors have been very, very widely developed. So biosensors are present in all these, very, very important industries. But please try to attach this to the definition I was trying to give. Biosensor is something that does anything associated with life. So all that I have listed here, it could be drugs, it could be disease, it could be environment, it could be the soil on which we, live and grow our crops, or it could be the food that we eat. Food and disease is a very, very big industry. And see, if somebody can package some food and say it is there on shelf for 8 months, no problem. So that means obviously he has to use some biosensor back at his place to quantify this measurement and then prove that, this will have a good shelf life of 8 months. Otherwise, you can't go to the market, right? And even in the biological warfare, this is important. Water is very important. So in every field, biosensors are very, very predominantly used. And if you look at the global biosensor market, 53% of that is largely because of the clinical diagnostics. I have been telling you that. So in fact, that was the very first industry why people started developing biosensor. Then 11% of that is for medical instrumentation. So then around 11% again for the industrial processes control, like the beverage industry or other industries where they use biosensors. So then around 8% for the veterinary and agriculture, then 6% for the defense, 5% for environmental, and 3% for research, and 2% for robotics, and 1% of other, which includes some miscellaneous fields, right? So biosensors are predominantly used for the health monitoring purposes. And if you look at the biosensor market research blog, so this is the data for 2020 prior to the epidemic. If you look at it today, probably it will be almost double this. So the blogs on biosensor market have been exponentially increasing thanks to the personal healthcare that we have been talking about. So the extent to which we talk about health and health conditions and safety are almost 10 times more than what we used to speak about when we all were kids. We had not heard of anything other than Saridan and Anasing. Right, our generations, right? But today, if you talk about it, so the concerns have increased, the problems have increased, and the solutions are also increasing, thank God. And if you look at where does India stand in the global scenario, when it talks about the publications in the field of biosensors, this is based on the first author from India or the country to which he belongs to, based on this particular paper. On domain visualization by the set of authors called Olson and Juhi Bay, and India is in the 10th position based on the first author from India, and US is in the first state with 13,000 plus publications. I think this data was collected somewhere a couple of years before, but even today it could be okay. And this is based on the publication of the Web of Science indexed journals. And this is the way from 1960 to 2018 or so, the rate at which the censor papers have been published. And this small blue fellow shows the way he is trying to catch up with the parent. What is shown in this dark blue color is the biosensor market, and this is a sensor kind of a research publications. And so thank God, biosensors being an offshoot of the sensor technology, so they're also trying to catch up with the parental sensors. And things are enormously increasing, and I'm very sure the prospects of research in biosensors is enormous. There is more need for personal health care. There is more need to develop the so-called wearable biosensors, in which I can just wear the sensors and move around for various applications. So that's what the whole world is looking for today. Yeah, so I'm almost at the end of my talk. So to quickly summarize, we spoke about the small molecules, their sizes, their importance, and bad things and good things that they can do us. Then we spoke about the basics of biosensors, the components that make a biosensor, and we highlighted the importance of bioreceptors and the importance of immobilizing them for better stability using 5 different techniques, starting from entrapment to covalent bonding to cross-linking and to adsorption and so on. Then there could be 6 possible interactions between the bioreceptor and the analyte that are trying to look for, like enzyme, nucleic acid, and so on and so forth. And we took the standing out example of the antigen and antibody interactions that are very popularly used to detect the so-called coronavirus that has bothered the whole world. Rather than bothering, it has shook the whole world, and I wish it will go and people will be happy hereafter. And then we took the example of the evolution of the glucose biosensor, 1G, 2G, 3G, in which the journey of the electron from the GOX center to the electrode was simplified, as you progress from 1G to 3G. Then we looked at the impact of nanomaterials in biosensing applications, with amazing applications that they can bring about. And then we took the examples of cholesterol and DNA as the examples, and we looked at the fabrication process, and even the results were presented to impress upon the development of these sensors for the novel application of detecting cholesterol and DNA. Before I conclude, all that I discuss are the man-made resources, what you make, I make, or what the scientists make, or what the engineers make. But just look at what the nature has done. Mother Nature is beyond all this. So God or the mother is the greatest creator of all those things. Look what she has created. So a bear can sense food from a distance of 18 miles. So that is the kind of sensitivity God has given to this particular animal. And bees can find the most efficient route between flowers faster than even a supercomputer. That's all what we can say. The reason I often put these 2 slides at the end of my presentation is that, so if you are researching, or if you are an engineer, if you are trying to look at novel solutions, please look at nature from your take a closer look. And nothing could be more inspiring than what nature is. And everything that happens in the nature is a miracle. And be inspired by nature, and you can do a wonderful job, right? So with this, so thank you for your patient listening. And sir, I'll stop sharing, and if there are any questions I can take.
Yes, sir. Some questions is there, sir.
Yeah, can you ask it to me? I can't see the questions here. One second.
I'll tell you, sir. Sir, what is the difference between a biological signal and medical signal?
What is the difference between?
Biological signal and medical signal.
Okay.
Iranya Ranjan Thakur.
Okay. It's very difficult to differentiate between these two. Biomedical is about the signals coming from the human body. There is nothing called as a medical signal as such, right? So we don't study anything with the anatomy and physiology in the field of biomedical engineering. Biomedical engineering is an application of the electronics and computer science to extract the signals coming from the human body. So that could be signals like the EEG signal, ECG signal, EMG signal, EKG signal, ECOG signal, UOG signal, and things like that. So we try to make a measurement of this. And I have come across only biomedical signal, which are the if you go back to the way the cell works, there is something called as action potential. So that's where the whole thing begins. So an action potential is a small electrical pulse of 70 millivolts that is generated inside a particular cell, and all of them will integrate together and reflect on the body as an EEG signal, an ECG signal, and EMG signal. I don't know. I don't think I can classify signals as medical signals and biomedical signals. But to make some sense to the very good question, I have tried to differentiate between an action potential that is generated within a unit cell of a body, and then through the process of what is called as volume conduction, that will manifest itself on the surface of the human being as the ECG signal, EMG signal, EKG signal, and so on, which we call as the biomedical signals. So did I make some sense to your question?
Yes, I think I got. Next question.
Yeah.
Whether you can buy biosensors for research work. VC Kumar.
Come again?
where we can buy biosensors for research work from VC Kumar.
Okay. There are biosensors commercially available, but may not be in the stage of you doing further research on that, because the commercial biosensors are all devices with everything fabricated. But of course, we can always get in touch with people who work in the domain of nanotechnology and see if we can fabricate our own device to do research on this particular topic. But the research papers, they're all available there. But I don't think, the bare biosensors in which you can have these nanorods available and given to you to make some sensing, I doubt them being available, because once they're commercialized, it gets packed into the whole device with all the instrumentation, electronics and things like that. For research, there is no other way for you to fabricate your own device and come out with some novel observation.
Okay, sir. What are the biosensors used in pulse oximeter?
A pulse oximetry is not based on a biosensor. It is based on what is called as a measurement of the blood volume changes as we respire and, as we inhale and exhale at the fingertip. So there is a change in the blood volume that is happening. And based on that, they measure the ratio of what is called as the saturated oxygen to the unsaturated oxygen in the blood. It is not based on any biosensor application. They use a set of, light sources and light detectors, which can differentiate between the reflection because of the saturated oxygen in the blood and reflection because of the unsaturated oxygen in the blood. When they take the ratio, you have the SpO2 reading, which is called as the saturated oxidation level. It is not based on a biosensor. It is based on a wearable sensor, which is used to sense the biological signals.
So one more. Where are the nanowires are used?
Nanowires, as I try to give an example here, based on nanowire, people have developed, sensing technique to measure cholesterol. So similarly, you can find very numerous applications of golden nanowires or any nanowire for that matter to detect all these samples.
Hello.
Sir,
Yes, sir.
Russia has developed.
Yes, sir.
Russia has developed Sputnik 5
Yes, sir.
vaccine. What they have told is not T-cell technology. If you know any technology, what they have used, not antibody technology maybe, like Oxford.
Yeah, sir. I mean, many of the techniques, they take some time come to the public. And some of the things, if anything which has got to do with the intellectual property, it's very difficult for us to know well in advance. So what all that we discussed so far is what is available as in the form of an open literature. So maybe it will take a few, years for us to know what actually Russia did to come out with, those kind of sensors or techniques.
Okay, thank you.
Yes, sir. Welcome.
Sir, some more question is there. Shall I ask?
Yes, sir. Please.
Wristwatch-based biosensors are gaining much application in optical devices, accurate results like heart rate and oxygen rate monitoring.
Okay.
I think they are not completed. Then, are MEMS more useful for cellular research or NEMS?
See, MEMS are microelectromechanical devices. NEMS are nano-electromechanical devices. So as you go down to lower scales, the performance obviously will improve. But the sets of fabrication challenges will also increase enormously, right? So it's very difficult to say whether NEMS is better or MEMS is better. It all based on the application. A NEM device can give better performance than a MEM device for some X application, or it could be the other way for a different application, right? So NEMS is the next level of MEMS, I can say. But fabricating devices is extremely difficult. Obviously, they will become more sensitive because you're going to the nanoscale right away. The other problems could be, in their durability and their deployability and things like that. But if you ask me, the more bottom you go, the better will be the response, obviously. So NEMS may be quicker to respond or more sensitive than MEMS devices.
So one more question.
Yes, sir.
How can differentiate between biochip and biosensor?
Biochip and?
Biosensor.
See, a sensor, we know what it does. Biosensor I have talked about at length today, which is used to detect a biomolecule. When you talk about a biochip, it can do the whole lot of things. For example, if you look at what is happening in the wearable electronic industry, the people talk about a lab on a chip. People talk about a wearable lab. It means that, for example, I can, wear some kind of a wristwatch that has got a biochip, which does measurement using a suitable biosensor, which will condition that, which will manipulate that, which will make it into a wireless communication device and communicate it to another place that is available elsewhere. One possibility. Another possibility could be it could analyze in detail and give me even more meaningful information, right? So sensor is a part of a bigger system, right? If you talk about a lab on a chip or a system on a chip, that can do much more than what a sensor can do. It could be having some intelligence into that. It could have an ability to analyze the things and so on and so forth. So that is high end of that.
Okay, sir.
Yes.
Okay, thank you, sir.
Yes,
and,
sir.
Thank you for playing.
Yes, sir. Yes, sir. Your voice is breaking anyway. My pleasure. And
thank you, sir, for giving such energy after collecting our glucose. In depth, we gone to that. What is the biosensors?
Yes, sir.
And
yes, sir.
participants get maximum benefit. Even if today with myself I come across that what is the difference between what is the nano sensor actually? Why it is called as nano sensor?
Okay.
Clearly.
Yes, sir.
Cleared our doubt.
Yeah, my pleasure, sir. It's very difficult to keep that.
Nice.
Yeah, sir.
It's nice presentation.
Yes.
Hello,
Hello.
sir.
Yes, sir.
Hello, sir. I'll unmute again. Sir, BP, sir. Hello.
Yes, sir.
Hello. Unmute. Sir, BP, sir. Hello, sir.
Hello.
Yes, sir. Yes, sir. We can hear you now.
Sir.
Yes. Tell me, Professor HPK.
Sir.
Hello.
Hello.
Hello. Hello. Yeah.
Sir, we can hear you.
Professor Prasanna.
Yes, sir.
Thank you very much, sir.
Sir, my pleasure, sir.
Sir, please unmute yourself, sir.
You didn't hear me now?
Now he's hearing, sir. Please tell. Please.
No, you can. Yes, sir.
Sir, carry on, sir.
Okay. Thank you very much, Professor Balakrishnan, sir, for your wonderful exposition of biosensors.
My pleasure.
Research in biosensors and various concepts that are associated with biosensors. Thank you very much to electrical engineering and all the participants. And I can see that all participants are very excited about your presentation. Thank you very much. Over to you.
Yes, sir. My pleasure, and thank you very much for the opportunity to share my knowledge with you. Thank you, sir.
It's our pleasure.
Thank you, sir. One question, sir.
Yes, sir. My pleasure, sir. Thank you.
Okay.
Yes.
Thank you, sir. I'll contact you later. Okay,
Yes, sir. Yes, sir. Please, sir. Thank you.
Okay, sir. Thank you for your eye-opening session, sir.
Thank you very much, sir.
Yes, sir. Yes, sir.
Thank you very much. Thank you, sir.
Okay.
Thank you.
Sir?
Shall I wait for 5 minutes and close the session?
Yeah. Mahesh?
Yes, sir. Yes, Professor.
ಇದಕ್ಕೂ ಹಾಕ್ಬಿಡ್ಬೇಕಾಯ್ತು ಅದು ನಮ್ಮ ವಾಟ್ಸ್ಆಪ್ ಗ್ರೂಪ್ಗೆ ಆಲ್ 3 ಸೆಷನ್ಸ್.
Okay.
Okay. Let them fulfill that feedback. Okay. I shall end the record. Yeah.